Good morning. So yeah, we're going to talk today about some of the challenges associated with high pressure recip compression with non-lube hydrogen. So we've talked about the evolution of the hydrogen market. I don't really have to repeat all the reasons, but we've gone through that quite a bit this morning. But we're driven by decarbonization targets. We see that hydrogen is an excellent source or energy vector storage medium for a lot of the green energy solutions that we're looking at now. But this drives a lot of new applications for reciprocating compressors, right? So a lot of the storage, transport applications, refueling, tank filling, pipeline. And that comes with its own set of challenges for a recip that is really broadening the range of what we expect a reciprocating compressor to do. So higher pressures, specifically non-lube operation, very clean, very dry gas. In a lot of cases, these are going to be small, high-speed units, a lot of start-stop operations. So all of these things complicate the operation of a recip compressor. And so some of the things that Burak and I will talk about is specifically what some of those challenges are and some of the things that we're doing to address those challenges. So again, why hydrogen? Greenhouse gas emissions are really driving us to new solutions. A lot of the renewable energy sources are variable, and so they require some type of chemical battery, which hydrogen does very well. It's very effective at that, and it can be used for a lot of applications. So home and industrial heat, power, global transport, or fuel cell vehicles, right? So we've kind of talked through some of those, and I'm sure we'll talk through some more of that today. But these are the things that are driving hydrogen. But when we specifically look at reciprocating compression, some of the challenges, it's our wrong button. We've said hydrogen's a tiny molecule. It's inherently difficult to seal. So if there is a leak path anywhere in your seal parts, hydrogen's going to find it and it's going to leak through at a much higher rate than, say, methane or other typical gases that we're used to compressing. So all the potential leak paths we have to minimize or eliminate. We have to look very carefully at clearances, tolerances of fit, surface finish. All of these things as we're designing our seal parts become a lot more critical. So our specifications around these are evolving as we move into this market. The limits of the wear materials, and this really is what Burak will go into a little bit more detail on, but the frictional challenges of high pressure and non-lube running surfaces are very challenging here. And then there's even an impact on just the material from exposure to high pressure hydrogen. How does that change the material inherently, right? And then the geometric challenges. So a lot of these units, because they're high pressure, we're looking at 300, 400, 500 bar discharge. You're getting into very small bores. So very small bore, high pressure. You've got to make small piston rings, small rod rings that are still robust and can stand up to that pressure. So that requires new robust designs that can do that with a small cross section. And it makes the heat management more difficult, especially in a higher pressure or higher speed, short stroke type unit, where heat removal becomes very tricky, right? So if we look at existing sort of traditional applications for non-lube hydrogen and recip compressors, we're usually over in this range, right? We've got a range of sliding speeds here, but typically the limit on pressure there is about 100 bar in more common non-lube hydrogen applications, right? But now, this market is pushing the limits way out here. So we see quite a bit in the 300, 400, 500 bar range where we're looking at, tank filling. But now, again, pushing all the way out here to 900 to 1,000 bar. Some of these are not your traditional recips. You've got some of the, slower speed hydraulic drive type units, but still the design of the seal components, the materials that you bring to bear there are still have a lot of overlap with reciprocating compressors. So this is really a challenge. We're pushing this limit way out beyond what it typically was. So in terms of the design of the wear parts, or at least the mechanical design of the parts, some of the things we're doing, so here's an example. I talked about the inherent difficulty in sealing a light mold-weight gas when you look at piston ring leakage. So we're doing a lot of bench testing here with different styles of piston rings under helium gas to really help optimize our piston ring selection and design. So for example, if you look at just a typical angle cut piston ring that you would have in a natural gas compressor, at different compression ratios here, you get a high degree of blow-by past your piston rings. And then say you take that down to more of a restrictive type step cut, lap joint, whatever you would call that, you can cut that leakage about in half. But that's still, for hydrogen, that's still a very high leak rate. So now we're looking at things like some unique twin ring designs that are more of a tight seal, positive seal, a little bit less prone to thermal expansion type issues that can cut that down by another factor of 3. So we can really continue to reduce that leakage. So we're continuing this work as we optimize our piston ring design and selection. And then we have similar tools that we're bringing to look at the packing. So as we look at packing, one of the things we look at is we'll look at how do we change the PV curve that you see in the cylinder to what you see in the packing, right? So this may be a typical PV curve that you would see in your cylinder. How do you smooth that out with the first couple of packing rings to reduce the stress and the load on your packing rings? So with hydrogen gas, the typical pressure breaker that you might put in that packing case isn't really having much impact here because the gas is just flowing through that orifice extremely readily and it's just not impacting that. So we're working on new mechanical designs that continue to bring that down and to smooth that out and ultimately get to a position where even with a high pressure swing in the cylinder, the peak pressures and the rate of change of pressure within your packing is minimized, right? So that increases your runtime on your packing, reduces the chance of premature failure, and allows you to run at these difficult conditions. But again, it's always going to come back to the wear materials, and that's really kind of the key to success with these types of applications. So for that, I'm going to turn that over to Burak to talk to us.
Thank you, Craig. So I understand I'm the last person between you and the lunch, so I'm going to try to make it very quick. I have quite a bit of data to show. I'll make sure we're on time. So, as Craig mentioned, as some of the previous presenters mentioned, materials will be the key current gap for successful compression of hydrogen at high pressures, and especially for non-lubricated conditions. So, we're going to be looking at some of the existing materials, some limitations, and see what we can do about them. So, I'm going to be explaining some of the limitations using the example of PTFE or Teflon. I think most of you are aware of this material very well. So this is the most common material we use in advanced sealing applications for dynamic applications. And there's a great reason for that, so it's a great material. So first of all, it has an excellent elastic response, so when you apply a load on PTFE, it will try to respond back, bounce back, so that creates a wonderful sealing restoring force. It can be used as a seal grade efficiently. Then it has excellent tribological properties as well. So during the rubbing action, PTFE lays a transfer film on the counter surface, so generates a PTFE on PTFE contact, which has one of the lowest coefficient of frictions of all the materials available to us in a practical manner. So very good friction and wear material. It is not a very stiff or a strong material inherently, but by utilizing very common fillers like carbon or glass, it can be made stiff and strong and creep resistant. So that's a problem that can be solved very easily. But at the same time, we are expecting that we will have some issues or some limitations on the use of PTFE, especially when we are dealing with the pressures mentioned in the previous slides, like 350 bar and beyond. So I'm going to use in the next few slides some analytical approaches, some theoretical models and experimental data to show what kind of a problem we have with this material and see how we can apply the same principles on the other materials to guide our research for newer technologies. Now I have a little bit of a complicated model here, but starting with the contact pressure, I'd like to give you a description of some issues we may have with PTFE. So here we have a model of a rod ring. So this is the cross-section of a rod ring. So in our model, we will use the geometrical parameters defining this rod ring geometry, which is the inner radius and the thickness and the axial length of the seal. And it's rubbing against the rod. And we are trying to determine this contact pressure or estimate that contact pressure under the effect of this effective gas pressure. So this gas pressure is actually given by a function of the inlet pressure of the gas and also the discharge pressure of the gas. So for our case here, we are using hydrogen, and the effect of the gas is included in the specific heat numbers here. So this is coming from the hydrogen itself. And for this example, we are using a discharge pressure of 350 bar and inlet pressure of 150 bar. So this gives us an effective pressure we will use as our loading pressure on the ring. And one other thing I need to make a note of is this: some of the geometrical parameters like the radius or the height of the sample is time dependent in this process, because as you wear out the sample, the radius will change, so that's also taken into account in this model. And when we plug all the numbers in the model and we get the contact pressure estimates for 4 different grades of PTFE, these are some of the numbers we get with respect to different wear levels on the ring itself. So just very quickly, if you look at the 0.25 millimeters of radial wear on the ring, we are averaging at around 23 to 28 megapascals of contact pressure. So what does this mean? So typical yield strength for PTFE grade, so when you run a compressive strength test at room temperature, you get 15 to 20 megapascals. So this is way higher than that level. So that means when you apply this much of a contact pressure, the material will eventually fail and have some plastic deformation and eventually lose the sealing efficiency and fail in the process. Then we go to the temperature effect. So in this case, I'm trying to estimate the temperature that's generated on the contact surface or the interface because of the rubbing action and the friction that's going on. To do that, I'm estimating the frictional force by utilizing the coefficient of friction, the load on the ring, and also the relative velocity of the contact pair. And this actually goes into this formula. We have the estimation for the maximum temperature we will get. And this also takes into account the thermal properties of the material, like the conductivity and the diffusivity of the material with respect to that gas. And again, by putting everything together and combining with the previous model, which can be explained in terms of the contact pressure, this load can be explained in terms of contact pressure, we get a combined curve, again, an estimate of the maximum temperature we will estimate on the contact zone. Now we are looking at very high temperatures, up to 400, 450 C level, especially for the glass fiber grade, which has the highest coefficient of friction between those 4 grades here, and also the lowest thermal conductivity, so the heat does not have a place to go, so it just stays in the interface and generates a very high temperature. And our maximum continuous service temperature, this is the recommendation for PTFE, that's around 250 C, so that's very low compared to what we are getting at an estimate for the temperature. So pressure is a problem, temperature is a problem, PTFE and its grades, however complex they are, they will not be sufficient for hydrogen compression at these pressure levels. Now, what can we do? So, one obvious way is to go even to higher temperature materials. So we have several good options, such as PEEK, polyimides or polyamide imides or Torlons you can see here. They have an experience level up to 250-300 C range, so these are very good candidates to consider in the next round. So let's look at some comparative data in comparison with some of the advanced PTFE grades here. So I'm looking at flex modulus as a measurement of the mechanical properties at 200 degrees C. And you can see the PEEK and polyimide excel or is actually greatly improved over the PTFE grade here. And also, let's look at the creep results. So this is a measure of the flow properties. So it's the amount of flow with a constant load at 200 degrees C. And again, with polyimide and PEEK, and even with the polyamide imide, so you get great improvements compared to the PTFE. So lower levels of flow associated with the deformation. So again, these are really good candidates to consider. But unfortunately, the selection process or making sure they will work is not very straightforward. So this is actually a graphical representation of the optimization game we are playing. So I'm using a single merit index here. So I'm dividing the flex modulus I measured in the previous slide to the creep strain. So the higher the number is better for us in theory. And I'm plotting all of my values for 5 different grades here. And again, we get the highest numbers with the PEEK and the polyimide. And I'm dividing the section into 3 groups. So you have the region A here, which is actually a collection of the materials that are not going to be tolerant to high pressures or high temperatures. So the PTFE is going to fall in this range. But at the other end, at the extreme end, we have to be concerned about the sealing efficiency. Now, you are going to be working with very high stiffness materials, which may not be a good sealing material because they may not have enough elastic response. So they may be too stiff, too hard to seal a gas like hydrogen. So we are in the process of defining these limits, these boundaries for all of these grades. So this is just a random representation of the optimization game here. But again, the higher the numbers do not necessarily mean these are the best materials yet, but we are working on that part. Now some data coming from our wear testing. So this is coming from a very specialized test equipment. We actually put our tribometer in a pressure vessel. We put a high pressure hydrogen, pressurize the gas to 4,000 psi, and we run the wear testing in reciprocating mode. And we get the wear rates for 4 different materials again. So in terms of wear rates, so you see some of the numbers are higher and some are lower, but these we consider falling into the same order of magnitude, and we consider all of these materials have some kind of a similar wear rate in high pressure hydrogen. And we also have a little bit of data coming from the air at the same exact conditions for PEEK, so we are also seeing a similar level. So at these conditions, at this wear testing, it seems like the high pressure hydrogen is not affecting the wear behavior of the materials, and we are not able to differentiate any of these materials with respect to their tribological properties. But one important note is the linear speed we use because of the limitations of the equipment we have. Note that that's inside the pressure chamber. we cannot really go too fast with our motion, so this is a very slow speed compared to what we find in compressors. And a slower speed generally does not make a lot of frictional heating, so it may be an important factor to have this set of data. So with a higher speed wear testing, you may have a different result. So that's something we are working on. Another interesting note coming from this test is on the plot on the right side. So this is what we observed on our samples. So our samples, when exposed to high pressure hydrogen, pretty much from all of these materials, continue to grow for about 24 hours. So this is a plot of their dimensional change. So as they absorb more and more hydrogen, their growth continued, and we got a stabilization at around 20 hours. So that's when we could start our wear testing actually. So we had to have a stabilization process before the testing. But this is also very important because if you have this much of gas going inside the material, should we be concerned about the effects of that gas inside the material, and if there is any degradation process going on with our materials of interest. And that's our next slide. So we also did some exposure testing at high pressure hydrogen with several of these materials. And on these plots, I'm showing the results from compressive modulus at different pressure levels. So you have the before tests here. You have 50 bar exposure tests for 150 hour long test and at 150 degrees C, and 100 bar test in this range. So for on-field PTFE, you can see the compressive modulus is actually before and after test drops by about 37%, which is very significant. So there's something going on with PTFE. And then if we go to a standard wear grade with PTFE, we see a similar decrease. Again, some softening is happening on the PTFE side, some changes in the properties. But interestingly, if we go to the peak poly limit or the premium wear grade of PTFE, we don't see any kind of a change. So that's really interesting, and we think these thermoplastic materials we have here, those are meltable materials, and this PTFE here is also a blend which also has some kind of a thermoplastic inside, is probably helping with the detrimental effects of the hydrogen in these cases. So more work needs to be done to understand what's going on with PTFE, but I think this is an important topic to consider. So as a summary, we talked about PTFE. We showed some of the limitations for high pressure hydrogen compression in non-lubricated situations. So we definitely think some geometry changes on our designs and some new materials are needed. We have some good options with existing materials, but we may also have to come up with next generation materials to do the job. And definitely further testing is required, especially to understand the properties in pure hydrogen. Also for dry and wet applications, you need to do the testing in wet hydrogen. Understanding tribology and wear rates in hydrogen and at high speeds is very critical. This is something we are working on as well. And finally, we need data from full compressor tests. So that's combining all the effects together with the application condition. As Dover precision components and Cook compression, we have been investing a lot in our infrastructure for testing in hydrogen. So we now have a hydrogen lab added to our facility in Houston, so we can do hydrogen testing. And we are working on some advanced hydrogen wear testing capabilities as we speak, as well as some high pressure exposure testing is going on. And we have a very strong team of materials to develop the next generation materials to tackle these challenges. So we are looking forward to addressing these issues, and we look forward to working with some of you guys in the challenge. Thank you very much, and we'll be available for any questions. Maybe now, maybe after lunch.
All right, I think we have time for one question. Good presentation. A couple of questions. What kind of surface finish did you have on the seal or the mating component? What type of seal was this? Was this a lip seal, spring energized seal?
Well, all of my experiments are not done on particular seal shapes, but samples on coupon shaped. But when we do the wear testing, we try to match the surface properties of the counter surface with the application conditions. So the material or the surface finish, hardness, all those things are generally fed into us through the application steam. So they should be pretty relevant.
All right, thank you, Burak. Craig, can we have a round of applause?